Across the universe, some stars spin so fast they flash like cosmic lighthouses. These are pulsars. Born from the collapse of massive stars, they beam light with perfect rhythm across the endless dark. Tonight we'll uncover what makes them so mysterious and mesmerizing. If you enjoy this journey, please like, subscribe and share, and tell us in the comments, what do you think drives these cosmic beacons? Thank you for watching. Now, let's begin. Across the vast plain of the Milky Way, amid the background hiss of interstellar radio noise, a faint rhythmic signal once appeared, precise, unwavering, and unlike any known source in the sky. It was the late 1960s, and radio astronomy was beginning to open a new window on the universe. Dishes and antennas sensitive to invisible wavelengths began mapping the galaxy's diffuse radiation. Among the long drifts of static, one observatory in Cambridge detected a pattern that repeated every 1 1/3 seconds, so exact that it seemed mechanical. At first, the signal puzzled observers. It neither flickered like a quasar nor drifted like interference from Earth. Each pulse arrived with such regularity that it was timed to fractions of a millisecond, an astonishing precision, from an object many thousands of light-years away. As further detections followed, scientists realized that this was not an anomaly, but a new class of celestial source. Later called pulsars, these cosmic timekeepers would soon reshape the understanding of stellar death and matter at its densest state. The discovery came during an era when the Milky Way was being mapped in radio light. Beyond the visible stars lay clouds of hydrogen-cold dust and relic radiation, left from ancient processes of stellar birth and decay. Radio telescopes traced vast arcs of emission from supernova remnants, expanding shells left by exploded stars. The first pulsar signal appeared within one of these regions, hinting at a connection between dying stars and these new radio beacons. What began as a curiosity soon revealed a pattern across the sky. More pulsars were found, each with a slightly different pulse period, some slower, some faster, all steady beyond expectation. Each object appeared as a single point of radio emission, brightening briefly as if a rotating light swept past the Earth. To understand their origin, astronomers considered the forces that could produce such stability. A mechanical rotation seemed likely. Nothing else could yield a periodic signal so consistent. Yet for a star-sized body to spin once every second without disintegration, its density had to be immense. The idea of a neutron star, first theorized decades earlier, suddenly found observational proof. These were stellar cores left behind after supernova explosions compacted until protons and electrons fused into neutrons. Such objects pack the mass of a sun into a sphere barely 20 kilometers across. The surface gravity reached levels far beyond any laboratory condition, and the magnetic fields were thousands of billions of times stronger than Earth's. The combination of rapid rotation and intense magnetism produced narrow beams of radiation from the magnetic poles, and when one of those beams crossed Earth's line of sight, a pulse was observed. The universe had revealed a kind of natural clock, whose precision rivaled man-made instruments. Early radio data showed that each pulse was nearly identical in shape, repeating over hours, days, and months. Even the faintest variations offered new clues. When the signal seemed to drift slightly, it was not the star itself changing, but rather the radio waves being delayed as they passed through clouds of electrons between the stars. This allowed astronomers to measure the density of interstellar plasma and map the hidden structure of the Milky Way. Pulsars thus became not only exotic remnants, but tools for studying the medium that filled the space between stars. The early catalogue of pulsars expanded quickly. Within a few years, hundreds had been identified scattered throughout the galactic disk. Most lay within regions dense with past star formation, where massive stars had lived short, violent lives and ended as supernovae. A few were found outside the plane high above or below the galactic midline, possibly kicked outward by the asymmetric force of their birth explosions. Each new discovery refined the understanding of how energy and matter circulate in the galaxy. Radio astronomers learned to track the arrival times of pulses with extraordinary accuracy. By comparing them against atomic clocks, they could detect the smallest variations. Some pulsars slowed down, gradually losing rotational energy as they emitted radiation. Others spun faster than expected, particularly those later found in binary systems, where matter accretion could accelerate the spin. These observations began to form a continuum from young energetic pulsars in the remnants of recent supernovae to older, slower ones whose energy output had diminished. The population reflected stellar life cycles on galactic scales. The discovery of the first pulsar in the Crab Nebula provided dramatic confirmation. At the center of that supernova remnant known from records of a bright explosion seen on Earth in the year 1054, a compact source emitted pulses 30 times per second. This Crab pulsar showed clearly that pulsars were the remnants of massive stars that had died in explosions visible even to ancient observers. High-speed photography and later X-ray observations revealed a rotating beam sweeping across the nebula, energizing the surrounding gas with each turn. The visual connection between a supernova remnant and a pulsing neutron star completed the narrative of stellar death and rebirth in the galaxy. As instrumentation improved, telescopes began detecting pulsars beyond the radio spectrum. Optical flashes were observed in the Crab pulsar, followed by detections in X-rays and gamma rays. This wide range of emission confirmed that the mechanism driving the pulses was highly energetic, involving charged particles, accelerated to near the speed of light in strong magnetic fields. The pulsar's light was not produced by thermal heat, but by electromagnetic processes unique to these compact objects. Each rotation sent streams of radiation outward in narrow cones, visible only when aligned with Earth's direction. The analogy of a lighthouse was apt, though the physical process was far more complex. By the time pulsars became a recognized population, they had already begun to influence several branches of astrophysics. Their extreme stability made them valuable as natural time standards. Networks of observatories compared pulse timings across the world, building detailed models of their positions and rotational behavior. Minor irregularities sometimes revealed unseen companions, allowing the discovery of binary pulsars long before optical confirmation. Through these observations, the motion of pulsars around companions provided the first precise test of general relativity in strong gravitational fields. The timing variations matched predictions of gravitational wave emission, long before such waves were directly detected. The early decades of pulsar study also reshaped ideas about the galaxy's energetic environment. Pulsars explained certain mysterious radio sources, once thought to be entirely different phenomena. They contributed to the population of cosmic rays influencing the chemical makeup of interstellar space. Some served as anchors for understanding magnetars, a later subclass, with even stronger magnetic fields and irregular bursts of radiation. Step by step, what began as an unexplained radio pulse evolved into a foundation for modern high-energy astrophysics. Today, the first discovery is remembered not for its initial confusion, but for the doorway it opened. The faint repeating signal that once stood alone in a sea of static is now one voice among thousands, each one a turning neutron star transmitting a pattern of light across space. From the outer arms of the Milky Way to the dense clusters near its core, pulsars trace the cycle of stellar evolution and illuminate the invisible structures of the galaxy. Their discovery marked the beginning of a new precision in astronomy, a rhythm of cosmic rotation that continues to guide observation half a century later. A pulsar begins where a massive star ends. For most of its life, a star balances gravity pulling inward against pressure from nuclear fusion pushing outward. In the deepest regions, hydrogen fuses into helium, and later as the star ages, helium fuses into heavier elements. When the core becomes iron, the process halts. Iron cannot yield energy through further fusion, and without that energy, the pressure that supports the star collapses. Gravity no longer resisted drives the core inward with immense acceleration. Temperatures rise to billions of degrees, and atoms are crushed until their electrons merge with protons forming neutrons. In a fraction of a second, the core shrinks to the size of a small city. The outer layers, suddenly unsupported, crash inward and rebound violently. A shock wave races outward, tearing the star apart. The explosion is a supernova, a brief brilliant flash that can outshine an entire galaxy. What remains at the center is a dense remnant, the neutron star. This process releases more energy in seconds than the sun will emit in its entire lifetime. Neutrinos stream outward in vast numbers, carrying away most of the gravitational energy. The newly formed neutron star is born hot and rapidly spinning its surface, glowing at millions of degrees. Around it, the expanding debris of the original star moves outward as a supernova remnant, a shell of gas and dust that glows in X-rays and radio light for thousands of years. The transformation from ordinary star to compact remnant is both destructive and generative. Elements heavier than iron created during the explosion are scattered through space, enriching future generations of stars and planets. The structure that remains inside the collapsed core is unlike any ordinary matter. At its surface, the density reaches hundreds of millions of tons per cubic centimeter. Deeper within, atomic nuclei are packed so closely that their boundaries blur. The pressure is so intense that neutrons behave collectively, forming an exotic quantum fluid. In this compact sphere, gravity compresses matter to the limits allowed by physics. The radius of such a star is roughly 20 kilometers, yet it contains as much mass as the Sun. To escape its surface would require speeds approaching half the speed of light. Space-time itself is curved so strongly that light paths bend, allowing observers to see more than half of the surface at once. Immediately after formation, the newborn neutron star spins extremely fast. Conservation of angular momentum dictates that as the core's radius shrinks, its rotation speeds up much, as a spinning skater accelerates when drawing in their arms. A star that rotated once every few days before collapse may now spin several times per second. Alongside this rapid rotation, the magnetic field of the original star becomes vastly compressed. Magnetic field lines that once stretched across millions of kilometers are forced into a much smaller volume, amplifying their strength by many orders of magnitude. The resulting field becomes one of the most intense in the universe, channeling streams of charged particles along its poles and powering the emission mechanisms that define pulsars. The young neutron star, still surrounded by the debris of its parent supernova, exerts a profound influence on its environment. Its rotation generates electric fields that accelerate particles to near-light speeds. These particles collide with the expanding gas, producing synchrotron radiation that glows brightly in radio and X-ray wavelengths. Over time, as the surrounding cloud expands and cools, the remnant fades, but the neutron star endures. It gradually cools as it radiates heat, but its rotational energy remains immense. For thousands of years, it continues to spin rapidly, emitting beams of radiation from its magnetic poles. If one of those beams aligns with Earth, the neutron star becomes visible as a pulsar. In the first centuries after formation, the young pulsar's environment is turbulent. Magnetic fields twist through the expanding remnant, and particle winds carve cavities in the surrounding gas. Observations of the Crab Nebula show this vividly. At its center, the Crab pulsar injects continuous streams of particles that form filaments and wisps moving outward like slow waves of light. Each rotation of the pulsar refreshes this flow, maintaining the nebula's brightness nearly 1,000 years after the explosion. This enduring energy demonstrates how the rotational kinetic energy of a single neutron star can power a vast structure many light years across. Not all supernovae leave neutron stars behind. If the progenitor star is extremely massive, more than about 20 or 30 times the mass of the Sun, the core collapse may proceed past the neutron stage, forming a black hole instead. The threshold between these outcomes depends on the details of the explosion, the composition of the star, and the dynamics of the collapse. For stars in the intermediate range, where the remnant mass stays below this limit, neutron stars are the natural endpoint. The diversity of pulsars found across the galaxy reflects the variety of initial masses and explosion conditions among their parent stars. Supernova explosions also impart motion to their remnants. Because the collapse is rarely symmetrical, the newborn neutron star often receives a kick, propelling it through space at hundreds of kilometers per second. Some race through the galaxy at speeds sufficient to escape their birth clusters entirely. Others remain embedded within their remnants, gradually drifting outward as the surrounding gas disperses. Over millions of years, these compact remnants populate the galactic disk, each one a silent trace of a long-destroyed giant. The distribution of known pulsars today follows these patterns, with concentrations in regions rich in massive star formation. From an observational standpoint, the aftermath of a supernova offers multiple windows into the birth of pulsars. In optical light, astronomers see expanding shells of glowing gas. In X-rays, they observe the compact central source and its high-energy surroundings. In radio wavelengths, pulsations begin to emerge as the neutron star's magnetosphere stabilizes and its beams align through space. Each wavelength reveals a different layer of the process, from the shock-heated outer gases to the compact engine within. The study of these remnants provides a living timeline linking stellar death to the origin of pulsar signals detectable from Earth. The physical processes that occur during the first moments of neutron star formation remain among the most extreme known in nature. Temperatures reach billions of degrees, densities exceed atomic nuclei, and magnetic pressures surpass any terrestrial equivalent. Within seconds, the newborn star cools through neutrino emission, contracting slightly as it stabilizes. Crusts of dense nuclear material begin to form, while the interior transitions toward a superfluid state. The balance between gravitational compression, nuclear repulsion, and quantum effects defines the final equilibrium. What emerges is an object stable against further collapse, yet still dynamic enough to release energy through rotation and magnetism. In the quiet aftermath, the nebula expands, the shock front cools, and the pulsar continues to rotate. Its light sweeping through space carries the signature of its birth, a rhythm that began in the instant of collapse and endures for millions of years. The supernova marks both an ending and a beginning, the death of a massive star, and the birth of a precise cosmic beacon. Each pulsar seen today once blazed as a supernova, scattering the ingredients of new worlds, and leaving behind a spinning core dense enough to challenge the limits of physics. In the remnants of destruction, a new kind of order persists, a pulse repeating through the silence of interstellar space, the faint heartbeat of a collapsed star. The neutron star stands as one of nature's most compact and extreme creations. It is a sphere no larger than a city, yet within that sphere resides a mass comparable to the Sun. To describe it requires stretching the imagination beyond familiar experience. Its surface gravity is hundreds of billions of times stronger than Earth's, and a teaspoon of its matter would weigh as much as a mountain. The density is so great that atomic structures cannot survive. Protons and electrons are squeezed together until only neutrons remain bound, in a fluid that defies conventional description. This is matter in a state between the ordinary and the theoretical, held together by forces that dominate only under the most violent conditions in the universe. Viewed from the outside, a neutron star is smooth and small, an object only about 20 kilometers in diameter, yet its mass is supported by the degeneracy pressure of neutrons' quantum effects that prevent identical particles from occupying the same state. The crust is believed to be solid, a dense lattice of atomic nuclei surrounded by a sea of electrons. Beneath this crust, pressure increases until nuclei dissolve into a uniform mixture of neutrons with traces of protons and electrons. Deeper still, the matter behaves as a superfluid and possibly a superconductor, meaning that it flows without resistance and conducts magnetic fields perfectly. This strange physics gives the star its remarkable stability and influences everything from its rotation to its emission of radiation. The gravitational field around a neutron star is intense enough to curve light significantly. Photons leaving the surface lose energy as they climb out of the gravitational well, their wavelength stretched into the red part of the spectrum. Observers can see more than half the surface at once, because the curvature bends light paths toward them. This same curvature causes time to pass differently near the star than it does far away, an effect predicted by general relativity. For the pulsar signals we receive, these relativistic corrections must be applied precisely, or their timing would drift over years of observation. The magnetic field of a neutron star is another defining feature. It can reach strengths 1 trillion times greater than Earth's magnetic field. These fields shape the star's surroundings, confining charged particles into narrow funnels that channel radiation from the magnetic poles. The field also locks into the crust, so as the star spins, it carries the magnetic axes along with it. Because these axes are often tilted relative to the rotation axis, the result is a continuous sweeping motion of radiation through space. To distant observers, this appears as regular pulses of light, a pulsar's heartbeat. In describing the internal structure, scientists rely on equations of state models that relate pressure, density, and temperature at different depths. Yet because such conditions cannot be reproduced in laboratories, these models remain uncertain. Observations of neutron star masses and radii provide constraints. Most neutron stars weigh between 1 and 2 times the mass of the Sun. If the mass was smaller, the pressure would not be enough to counter gravity. If larger, it might collapse into a black hole. Measurements from X-ray binaries and gravitational wave events continue to refine these limits, revealing how matter behaves under nuclear saturation densities. Each observation narrows the possibilities for what exists inside. The outer layers of a neutron star form a rigid crust only 1 kilometer thick, made of nuclei arranged in exotic configurations, sometimes called nuclear pasta, because of their shapes, sheets, tubes, and clusters compressed by competing forces. Beneath this crust, the core extends downward through increasing densities, possibly reaching a region of free quarks or other subnuclear particles. In this inner core, theoretical physics meets its limits. It may host strange matter or phases of deconfined quarks, where the usual boundaries of particles no longer apply. These regions, though unobservable, directly influence measurable properties such as spin behavior and the frequency of starquakes or glitches. The magnetic and rotational energies stored in a neutron star far exceed those of any ordinary object. Even though the surface is solid, the crust may fracture as stresses build from differential rotation or magnetic tension. When that happens, the sudden rearrangement produces a brief change in spin rate, a glitch. The crust, though only a thin layer, plays a key role in linking the rigid outer shell with the fluid interior. Inside, the superfluid component can rotate through the formation of quantized vortices, tiny whirlpools that carry angular momentum. Over time, interactions between the crust and the superfluid cause subtle changes in the rotation speed, which astronomers monitor to study the star's internal dynamics. Neutron stars also possess immense momenta due to their rapid spin. A typical young neutron star may rotate several times per second, while the most extreme, known as millisecond pulsars, spin hundreds of times per second. Despite this speed, their shapes remain nearly spherical, flattened only slightly by centrifugal force. The balance between gravity and rotation defines a critical limit beyond which the star would shed mass, but most remain safely below this threshold. The result is a nearly perfect equilibrium, compact, balanced, and extraordinarily durable. The surface of a neutron star emits heat long after formation. As it cools, radiation shifts from X-rays toward ultraviolet and eventually to optical wavelengths, though few are visible directly. Cooling rates depend on the composition and the presence of superfluid layers that conduct heat efficiently. Some stars cool faster through enhanced neutrino emission from their cores. The study of cooling curves, plots of temperature versus age, gives clues to interior processes. Every photon escaping the surface carries information from deep within, making neutron stars natural laboratories for nuclear and quantum physics. The gravitational pull at the surface binds even light elements tightly. If hydrogen or helium fall onto the surface from a companion star or the interstellar medium, they form only a thin atmosphere, perhaps a few centimeters thick. This atmosphere modifies the emergent spectrum and polarizes the outgoing light, according to the magnetic field direction. Observations with X-ray polarimeters are beginning to test these predictions, offering rare glimpses of the conditions at the star's surface. Each detection of polarized emission confirms that light escaping from these objects retains the imprint of extreme magnetism and gravity. Despite their violence in origin, neutron stars are remarkably stable once formed. Their rotations persist for millions of years, gradually slowing as they radiate energy. The spin-down rate measurable from timing data allows astronomers to estimate their ages and magnetic field strengths. Combined with location and motion data, these parameters trace back to their birthplaces in supernova remnants. Over time, the pulsar population provides a galactic census of stellar deaths, revealing patterns of star formation and destruction across cosmic history. In essence, the neutron star embodies the balance between collapse and resistance, between gravity's inward pull and quantum pressure's outward push. It is a boundary object, neither ordinary matter nor a black hole, existing in a regime where both relativity and quantum mechanics must be applied simultaneously. Everything that defines a pulsar, its precision, its radiation, its place in astrophysics, rests on this foundation. The star is both monument and experiment, a remnant of catastrophe, stabilized into a rhythmic beacon. Within its dense heart, neutrons move in a silent quantum sea, and every pulse we detect is a faint reminder of their collective motion. When the collapsing core of a massive star contracts into a neutron star, the principle of angular momentum ensures that rotation quickens dramatically. A body shrinking to a fraction of its former size must spin faster to conserve rotational energy, just as a skater accelerates by drawing in their arms. In the case of a star, this change is extreme. What once took days to rotate may now occur many times per second. The newborn neutron star emerges as one of the fastest spinning natural objects in existence, its rotation carrying immense kinetic energy. Each revolution stores a fraction of the original star's momentum, concentrated into a dense, rigid form. The balance between gravity, internal pressure, and rotation defines its structure in the first moments of existence. This rapid spin not only stabilizes the star against further collapse, but also shapes every feature that follows: its magnetism, its radiation, and the rhythm of its pulses across the cosmos. The rotation of a neutron star is astonishingly stable. Its mass is distributed nearly symmetrically, and the dense matter inside resists deformation. This gives the star the properties of an almost perfect gyroscope. Once set spinning, it continues with minimal variation, slowed only gradually by the loss of energy through radiation and magnetic braking. Observations of young pulsars show that they can complete dozens of rotations every second, while older rejuvenated pulsars, those spun up through accretion, can rotate hundreds of times per second. In both cases, the rotation is consistent to a precision unmatched by most human-made clocks. Tiny irregularities occur only during specific internal events, offering windows into the strange physics of the core. As the star spins, its magnetic field remains anchored in the dense crust. The motion of conductive material through this magnetic field induces enormous electric currents. These currents accelerate charged particles along magnetic field lines and power the beams of radiation that define a pulsar. The field lines near the magnetic poles open outward into space-forming funnels through which particles escape. The regions where these lines intersect the star's surface are sites of constant activity glowing with synchrotron and curvature radiation. The angle between the magnetic and rotational axes determines how these beams sweep through space. If one crosses Earth's line of sight, the observer detects a pulse each time the star turns. This geometry transforms steady rotation into apparent flickering light. The rotational energy of a neutron star is vast but finite. As it radiates energy through electromagnetic and particle emissions, the rotation slows gradually. The rate of this slowdown, known as spin down, is measurable with extreme precision. It depends on the strength of the magnetic field and the distribution of plasma in the star's magnetosphere. By measuring how the pulse period increases over time, astronomers can estimate both the magnetic field strength and the star's age. A newly born pulsar spins rapidly, but over millions of years its period lengthens, until the emission mechanism can no longer sustain itself. It then becomes radio silent, a dead pulsar drifting unseen through the galaxy. This long-term evolution links the population of pulsars to the overall dynamics of neutron stars and their place within stellar life cycles. Rotation also affects the star's shape. Although gravity keeps the neutron star nearly spherical, centrifugal force flattens it slightly at the poles. The degree of flattening is small, only a few tens of meters difference in radius, but even this subtle distortion can generate detectable effects. As the star spins, any asymmetry in its mass distribution can emit gravitational waves, ripples in the fabric of space-time. These waves are faint, but future observatories may detect them, offering direct evidence of how matter behaves under immense compression. The possibility of such emission turns each rapidly rotating neutron star into a potential probe of both general relativity and nuclear physics. Inside rotation interacts with the superfluid components of the core. In ordinary fluids, rotation distributes smoothly, but in a superfluid it is quantized, occurring through the formation of tiny vortices. These vortices carry discrete units of angular momentum and arrange themselves in regular arrays throughout the interior. As the star slows, vortices migrate outward, transferring momentum to the crust. Occasionally, they become pinned to imperfections in the crystalline lattice of the crust-building stress until they suddenly break free. This event produces a measurable change in rotation rate known as a glitch. The study of glitches reveals how tightly the internal layers of the star are coupled, and provides indirect insight into the quantum behavior of matter at nuclear density. The energy released by rotation manifests in more than just radiation. It drives winds of charged particles, generates shocks in surrounding gas, and influences nearby magnetic structures. In systems where the pulsar resides within a supernova remnant, its rotation powers entire nebulae. The Crab Nebula remains luminous largely because its central pulsar converts rotational energy into expanding waves of energetic particles. Over time, this energy loss slows the star further, linking its spin directly to the brightness of its environment. The simple act of rotation becomes a cosmic engine capable of lighting regions many light-years wide. In certain neutron stars, the spin reaches truly extraordinary rates. Millisecond pulsars often found in binary systems can rotate more than 700 times per second. These extreme speeds arise not at birth but through later rejuvenation. As material from a companion star accretes onto the neutron star's surface, angular momentum is transferred, gradually spinning the pulsar up to higher rates. Such recycled pulsars demonstrate that rotation is not fixed at formation, but can evolve through interaction. They also serve as the most precise natural clocks known, their timing stable enough to detect gravitational waves from distant galaxies through minute shifts in pulse arrival times. Despite these variations, the fundamental mechanism remains the same. Conservation of angular momentum and magnetic braking govern a predictable evolution. Each pulsar begins its life, spinning rapidly, loses energy steadily, and eventually crosses into quiescence. The range of observed spin rates from fractions of a second to mere thousandths maps directly to this life cycle. Rotation links the violent birth of a neutron star to its serene later stages, bridging stellar death and the quiet ticking of cosmic timekeepers. In the broader context of astrophysics, the spinning neutron star represents a synthesis of fundamental principles. Gravity, magnetism, and quantum mechanics all meet within its dense volume. The precision of its rotation allows astronomers to measure phenomena that cannot be recreated elsewhere: time dilation, magnetic decay, plasma dispersion, and the influence of interstellar matter on electromagnetic waves. Every pulse arriving on Earth carries with it the signature of rotation, slowed slightly by space, curved by gravity, and stretched by motion. Through these signals, humanity reads the spin of distant stars as if listening to the heartbeat of the galaxy itself. As each rotation turns, the neutron star continues its steadier mission, marking time across cosmic distances. The spin that began in the dying moment of a massive star endures for millions of years, slowed by nothing more than the faint whisper of radiation. What began as chaos, the collapse of a core, the detonation of a supernova, settles into order. A rhythm emerges, precise and unending, a rotation that defines the pulsar's existence and lights the darkness between the stars. The magnetic field of a neutron star is among the most powerful phenomena known in the cosmos. It originates from the collapse of the progenitor star's magnetic field during the supernova event. As the stellar core contracts by a factor of thousands, magnetic flux is conserved, compressing the field lines into a much smaller volume. The result is amplification on a scale unimaginable. What began as a modest stellar field of perhaps a few hundred Gauss becomes a field trillions of times stronger. This magnetic intensity shapes nearly every observable property of a pulsar, from its radiation to its evolution. It binds charged particles, sculpts the surrounding space into complex structures, and interacts continuously with the star's rapid rotation to produce electromagnetic torque that gradually slows the spin. The magnetic field is not merely a feature of the neutron star, it is the primary mediator between its interior and the cosmos beyond. In most pulsars, the magnetic and rotational axes are not perfectly aligned. This misalignment is essential, for it creates the periodic flashes that define pulsars. The magnetic poles, where field lines emerge from the surface, act as channels for charged particles. As the star spins, these poles sweep through space like the ends of a bar magnet in motion. When one of these beams crosses the line of sight of an observer on Earth, the radiation is seen as a pulse. If the axes were aligned, the beam would remain fixed and invisible. Thus, the geometry of misalignment transforms steady electromagnetic emission into a rhythmic signal. The angle between the two axes varies widely across the pulsar population, and this variation accounts for differences in observed pulse shapes, durations, and polarization. The structure of the field itself is dominated by a dipole pattern near the surface, similar to that of Earth's magnetic field but vastly stronger. Closer to the star, these lines are anchored in the crust, where electrical conductivity is near perfect. Farther out, they stretch into the magnetosphere, a vast region filled with plasma co-rotating with the star. Within this magnetosphere, particles are trapped along magnetic field lines and accelerated to relativistic speeds. The motion of these charged particles produces curvature radiation, which spans a wide range of wavelengths from radio to gamma rays. The precise mechanisms of this emission depend on how the magnetic field channels and energizes the plasma, and on the altitude within the magnetosphere where the radiation originates. In the inner magnetosphere, dense charges form a corrotating region known as the closed zone. Beyond a certain distance, where centrifugal forces exceed magnetic binding field lines, open outward, carrying streams of plasma into interstellar space. This boundary, called the light cylinder, defines the distance at which corrotation speed would reach the speed of light. The magnetic field beyond this boundary cannot maintain its closed loops, so it opens into a spiral pattern, carrying energy outward as electromagnetic waves and particle winds. The interaction between these open and closed regions establishes the pulsar's electrical circuit. Currents flow along magnetic field lines, returning through the outer magnetosphere and completing a global loop that extracts rotational energy from the star. The strength of the magnetic field determines how quickly this energy loss occurs. Young pulsars with stronger fields lose energy rapidly and slow their rotation within tens of thousands of years. Older, weaker field pulsars evolve more gradually, maintaining stable spins over millions of years. In extreme cases where the field exceeds 100 trillion Gauss, the object becomes a magnetar, a related but distinct class of neutron star capable of releasing sudden bursts of high-energy radiation as magnetic stress fractures the crust. These represent the upper limit of magnetic intensity achievable by matter before the field itself dominates the physical behavior of the star. The field also affects the physical properties of the star's surface. Magnetic pressure at the poles can modify the crust's shape, concentrating heat and altering emission spectra. Surface temperatures may vary from one region to another, depending on field strength and local conductivity. The strong field influences atomic structure, stretching atoms into elongated shapes and quantizing their energy levels. This leads to distinctive spectral signatures that can be observed with sensitive X-ray instruments. In this way, the magnetic field leaves an imprint on both the macroscopic rotation and the microscopic arrangement of matter at the surface. magnetic axis orientation evolves slowly over time. As the pulsar spins and emits radiation, electromagnetic torques act to align the magnetic and rotational axes. This gradual alignment changes the beam geometry, reducing the likelihood that the beam continues to intersect Earth's line of sight. Many pulsars fade from detectability for this reason, even though they continue to exist. The evolution of inclination angles contributes to the observed distribution of pulsars in the sky, and may explain why only a small fraction of all neutron stars are visible as pulsars. Within the crust, the magnetic field may decay through processes of ohmic dissipation and Hall drift. Electrical currents supporting the field encounter resistance, converting magnetic energy into heat. This decay is slow, often taking millions of years, but over time it alters both the field strength and configuration. In young pulsars, the field appears stable and dominates their emission. In older ones, as the field weakens, the radiation becomes fainter, and the star's role as a pulsar eventually ends. The study of magnetic decay links the population of pulsars to broader stellar demographics, showing how these compact remnants evolve from bright active objects to silent cooling spheres. The field does not remain isolated to the neutron star itself. It extends outward, coupling to the surrounding medium. When a pulsar moves through interstellar space, its magnetic field interacts with the plasma around it, forming a bow shock or wake that glows in X-rays and radio. These features, known as pulsar wind nebulae, mark the boundaries where the magnetized outflow meets resistance from interstellar gas. The shapes of these structures reveal both the direction of the pulsar's motion and the configuration of its magnetic axis. In this way, the field provides a visible trail through the galaxy, tracing the motion of the neutron star long after its birth explosion. At a more fundamental level, the existence of such powerful magnetic fields provides unique laboratories for physics under extreme conditions. In these environments, quantum electrodynamics predicts phenomena that do not occur elsewhere, such as vacuum birefringence, where empty space behaves like a prism, splitting light according to its polarization in the presence of intense magnetic fields. Observations of polarized light from certain pulsars may confirm these effects, offering experimental insight into quantum theory. Thus, the magnetic field of a neutron star not only drives its observable behavior, but also extends the reach of fundamental physics. Over time, the combined influence of rotation, magnetic alignment, and field decay dictates a pulsar's lifespan. The field begins as the engine of its brilliance, harnessing energy from the spin to produce radiation and particle winds. It gradually weakens its configuration, changing its power, fading. Yet even as it declines, it leaves a lasting signature across space trails of charged particles, luminous nebulae, and the steady imprint of electromagnetic precision in the signals that reach Earth. Every pulse we record carries within it the trace of magnetic order maintained against the pull of gravity. Through this balance, pulsars continue to shine as enduring testaments to the strength of invisible fields that thread the universe. The pulses that define a pulsar arise not from flickering but from steady rotation and geometry. Around the neutron star, magnetic fields guide charged particles into narrow beams that radiate outward from the magnetic poles. These beams are constant in the star's own frame, yet because the magnetic axis is tilted relative to the spin axis, the beams sweep through space as the star rotates. To an observer along the path of one of these beams, the radiation appears as rhythmic flashes of light. This is the lighthouse effect, the core of the pulsar phenomenon. The regularity of these flashes comes directly from the precision of the neutron star's rotation, transforming a continuous flow of energy into the appearance of discrete timed signals that can be tracked across years and even decades without measurable drift. In essence, the pulsar's beam is an electromagnetic spotlight. It arises where magnetic field lines open outward from the star's surface, forming acceleration zones called polar caps. Within these regions, intense electric fields pull electrons from the surface and accelerate them along curved magnetic lines at near-light speeds. As they spiral through the field, they emit radiation in tightly focused cones, aligned with their direction of motion. The rotation of the star then sweeps these cones through space. Because the radiation is highly directional, observers detect it only when the beam crosses their line of sight. This creates the illusion of pulsation even though the emission itself is continuous in the star's frame. Each pulsar's beam shape depends on the configuration of its magnetic field and the density of charged particles in its magnetosphere. The beam may consist of one or two bright regions corresponding to the magnetic poles, or it may include a complex arrangement of sub-beams and halos at different altitudes. Radio telescopes record these variations as differences in pulse width and shape. Some pulses are sharp and narrow, lasting only milliseconds, while others are broader and structured. The pulse profile remains stable over long periods, allowing astronomers to identify each pulsar by its unique fingerprint. Like a rotating lantern with characteristic edges, every pulsar displays its own consistent pattern of light and shadow. At radio frequencies, the emission is dominated by coherent processes, meaning that vast numbers of electrons radiate in phase, amplifying one another's signals. This coherence explains why pulsars can be so bright despite their small size and limited energy budgets. At higher energies such as X-rays and gamma rays, incoherent processes like curvature and synchrotron radiation dominate, producing smooth emission patterns rather than sharp spikes. These multi-wavelength observations show that the pulsar's radiation emerges from several layers within its magnetosphere, each governed by different physical mechanisms. The inner regions produce low-frequency radio pulses, while the outer gaps near the light cylinder emit high-energy photons. Together they form a lighthouse whose beam spans the entire electromagnetic spectrum. The periodicity of pulsars is astonishingly reliable. Each rotation corresponds to a measurable time interval, and deviations are minuscule. Astronomers can predict pulse arrival times years in advance with microsecond precision. This stability allows pulsars to serve as cosmic clocks for testing fundamental physics. Variations in pulse arrival times reveal subtle effects such as motion through space gravitational time dilation and dispersion by interstellar plasma. When multiple pulsars are timed simultaneously across the sky, their collective rhythms can even detect low-frequency gravitational waves stretching and compressing spacetime between them. The simple turning of a neutron star thus becomes a tool for measuring distortions of the universe itself. The lighthouse effect also explains the distribution of observable pulsars. Only those whose beams intersect Earth can be detected as pulsating sources. Many more neutron stars likely exist unseen, their beams aimed elsewhere. This selection effect means the true population of neutron stars is much larger than the catalogue of known pulsars. By modelling beam shapes and orientations, astronomers estimate that for every visible pulsar, several others remain hidden. As the star's spin slows and its magnetic axis aligns, the beam narrows and eventually fails to sweep past Earth at all, marking the end of its detectable life as a pulsar even though it continues to exist silently. Observation has revealed that some pulsars exhibit subtle variations in their pulse intensity and shape over time. These changes may result from shifts in magnetospheric currents or precession of the spin axis. In rare cases, a pulsar may alternate between active and inactive states, turning its beam on and off over intervals of days or weeks. Such behavior suggests that the magnetosphere can reorganize itself, altering the flow of plasma and the resulting radiation. Yet despite these minor fluctuations, the underlying rotation remains stable, maintaining the fundamental rhythm of the lighthouse. The beamed radiation from a pulsar interacts continuously with its surroundings. As the beam sweeps through space, it illuminates dust and gas, sometimes producing faint echoes detectable as delayed signals. In binary systems, the beam can strike a companion star or an accretion disk, causing additional emission at different wavelengths. These reflections provide indirect information about the pulsar's orientation and environment. Even isolated pulsars affect the interstellar medium through their particle winds, leaving behind elongated nebulae aligned with their motion. The combination of rotation magnetism and beam geometry thus ties the star to the larger galactic landscape. Polarization measurements reveal the geometry of the lighthouse in remarkable detail. As the beam sweeps past Earth, the orientation of the electric field vector rotates smoothly, tracing the path of the magnetic field across the observer's view. This rotation of polarization angle provides direct evidence for the rotating vector model, one of the earliest theoretical frameworks for pulsar emission. The model remains consistent with decades of data confirming that the changing angle of observed polarization reflects the geometry of a rotating dipole field. Through this method, astronomers can reconstruct the orientation of the magnetic axis and estimate the beam's opening angle. Even the timing of the pulses offers subtle insight. Because the pulsar's rotation is so stable, any slight delay or advance in pulse arrival time must originate from external factors. When the beam passes through clouds of ionized gas, lower frequency radio waves slow slightly compared to higher frequencies, a process known as dispersion. Measuring this delay allows scientists to calculate the amount of free electrons between the pulsar and Earth, effectively mapping interstellar plasma along the line of sight. The lighthouse not only marks time, but also probes the invisible structure of the galaxy, turning a distant beacon into a scientific instrument. As rotation continues over millennia, energy loss gradually weakens the magnetic field and widens the pulse period. The light fades, the beam narrows, and the pulsar drifts toward invisibility. Yet even after its beam ceases to reach us, the object remains cooling silently in darkness. The lighthouse effect ends, but its traces persist in the data collected over years of observation records of precise intervals that have helped define cosmic distance scales and refine understanding of relativity. The phenomenon that began with the alignment of magnetic and rotational axes evolves into a legacy of rhythm and measurement. In the grand view, the lighthouse effect transforms violent origins into order. From the chaos of collapse emerges a precise, predictable signal, a metronome of the cosmos. Each pulse that reaches Earth has travelled across light years shaped by gravity, filtered through plasma, and preserved by geometry. The steady rhythm of these beams speaks of stability in the midst of extremity. It is a reminder that even in the aftermath of destruction, nature constructs systems of enduring precision. The pulsar's beam, steady and unbroken, continues to turn, lighting the dark expanse with regular flashes that echo the rotation of a collapsed star, keeping cosmic time long after its birth explosion has faded from sight. A pulsar's radiation spans nearly the entire electromagnetic spectrum, from the longest radio waves to the highest energy gamma rays. Each wavelength reveals a different layer of the star's surrounding environment and the processes unfolding within its magnetosphere. What began as a discovery in radio astronomy has expanded into a unified view of emission, across all frequencies, showing that pulsars are not merely radio beacons, but complex multi-wavelength engines of radiation. Their energy emerges through distinct mechanisms operating at various altitudes above the surface, each one sculpted by the interplay of rotation, magnetism, and plasma dynamics. Together, these mechanisms form a coherent pattern of light that links the smallest scales of quantum motion to structures stretching hundreds of kilometers around the star. At radio wavelengths, the emission is coherent, meaning that countless electrons act in unison, producing waves that add together instead of cancelling out. This process requires precise conditions of density and motion, allowing charged particles to amplify one another's radiation, much as a laser amplifies light in a cavity. The result is an intense narrow beam capable of travelling immense distances through space without dispersing. Radio pulses are typically the sharpest and most regular of all pulsar emissions. They are produced low in the magnetosphere, close to the star's surface, where the plasma density is highest, and magnetic field lines are tightly curved. Observing their fine structure has allowed scientists to probe the geometry of these regions and test models of particle acceleration under extreme magnetic fields. As the focus shifts to higher frequencies, different physical processes dominate. In the optical and ultraviolet range, radiation originates from regions higher in the magnetosphere, where field lines open outward. Here, electrons moving at near-light speeds emit curvature radiation as they spiral along magnetic paths. These photons carry information about the shape and strength of the field and provide a bridge between the coherent radio emission below and the more energetic X-rays above. Only a handful of pulsars are bright enough to be detected in visible light, but those that are, such as the Crab pulsar display, precisely synchronized pulses across all wavelengths, confirming that the same rotation drives every band of emission. In X-rays and gamma rays, the emission becomes incoherent and dominated by individual particle interactions. Near the outer magnetosphere, gaps form where magnetic field lines cannot sustain a correlating plasma. In these gaps, enormous electric potentials accelerate electrons and positrons to extreme energies. Collisions between these particles and photons generate high-energy gamma rays through processes known as inverse Compton, scattering and curvature radiation. The resulting photons escape along open field lines, forming wide beams that often differ in shape from the radio beams below. Observations with space telescopes such as Fermi and NICER have revealed that the brightest gamma-ray pulsars often have weaker or absent radio pulses, implying that the geometry of high-energy emission zones differs from that of the lower-energy ones. The ability of a single object to emit across such a broad range of frequencies is tied to the vast difference in magnetic and electric field strength from the surface outward. Near the crust conditions are so intense that even vacuum behaves as a polarizing medium modifying photon propagation. At higher altitudes where field strength weakens, particle acceleration takes precedence, and the radiation becomes dominated by synchrotron processes. These transitions create a spectrum that extends over more than 15 orders of magnitude in frequency. Each part of the spectrum contributes to understanding how rotational energy is converted into electromagnetic output. Radio signals trace the near-surface plasma. Optical and X-rays trace the mid-magnetosphere. Gamma rays mark the outer gaps near the light cylinder. Pulsars also emit particle winds composed of electrons, positrons, and sometimes heavier ions. These outflows carry a significant fraction of the star's energy into surrounding space, forming nebulae that glow in X-rays and optical synchrotron light. The Crab Nebula, for example, remains bright because its central pulsar continuously injects energy into this wind. when the particle flow interacts with surrounding interstellar gas shocks, form heating the gas and generating non-thermal emission across multiple wavelengths. The study of these nebulae connects pulsar magnetospheres with their larger astrophysical context, showing how small rotating cores can influence regions many light-years across. Timing observations across multiple frequencies reveal subtle differences in pulse arrival times. Radio waves traveling through interstellar plasma experience frequency-dependent delays, while higher energy photons are unaffected. By comparing arrival times at radio-optical and X-ray wavelengths, astronomers can measure the dispersion of the interstellar medium and correct for its effects, refining pulsar timing models to microsecond accuracy. Multi-wavelength synchronization also provides clues to the spatial separation of emission zones within the magnetosphere. When pulses at different frequencies peak at slightly different times, it indicates that they arise from distinct altitudes or field geometries. These observations allow researchers to reconstruct three-dimensional models of pulsar environments, linking observed light curves to magnetic structure. Polarization offers another dimension of understanding. At radio frequencies, pulsar emission is often highly polarized, reflecting the ordered magnetic fields guiding the particles. As wavelength decreases, polarization tends to drop, suggesting that higher energy photons are produced in regions where field orientation varies more rapidly. Recent X-ray polarimetry missions have confirmed this expectation, detecting weaker but still measurable polarization in high-energy pulsar light. These results reinforce the idea that pulsars are dominated by structured magnetic fields, extending far from the surface, with emission properties determined by how those fields interact with moving charges. Some pulsars display transient phenomena that highlight the complexity of their emission mechanisms. In certain cases, sudden bursts of radio or X-ray energy known as giant pulses occur sporadically, exceeding normal intensity by factors of hundreds or thousands. These events last only microseconds, but reveal extreme coherence and energy density. They are thought to originate from localized magnetic reconnection events within the magnetosphere, where twisted field lines suddenly snap and release stored energy. Observing these bursts provides insight into the magnetic instabilities that can occur even in the seemingly steady environment of a pulsar. Other neutron stars produce bursts exclusively at higher energies. Magnetas with magnetic fields exceeding 100 trillion Gauss emit sporadic gamma-ray flares resulting from crustal fractures and magnetic rearrangements. Though distinct from standard pulsars, they share the same underlying structure, a rotating magnetized neutron star, and extend the multi-wavelength continuum to its most violent extreme. Between these extremes lie transitional objects exhibiting properties of both pulsars and magnetars, suggesting that the boundary between them is gradual rather than absolute. As instrumentation has advanced, the study of pulsars has become increasingly interdisciplinary. Radio arrays, optical telescopes, X-ray observatories and gamma-ray detectors all contribute to a unified picture of these objects. Observing a single pulsar across multiple bands allows scientists to follow energy as it flows from rotation to magnetosphere to interstellar space. The coherence of this system demonstrates the universality of physical laws under conditions far beyond human reach. Whether viewed as faint radio pulses sweeping rhythmically across the sky, or as high-energy flashes captured by orbiting satellites, pulsars express the same underlying process, the transformation of rotational kinetic energy into radiation through the mediation of magnetism and plasma. Across the electromagnetic spectrum, the pulsar reveals itself as both simple and complex. simple in its periodicity, which remains constant across frequencies, complex in its structure, which changes with altitude and energy. Each wavelength contributes a layer of understanding, much like instruments in an orchestra, combining to produce a single harmonious tone. The harmony of a pulsar's emission, coherent radio signals, glowing X-rays and cascading gamma rays, forms a cosmic composition that has played without pause for millions of years. Through these beams of light, we witness the endurance of energy and order in one of the universe's most extreme settings, a steady pulse of radiation carrying the silent story of a star's collapse into eternity. From the first discovery, pulsars astonished astronomers with their precision. Each pulse arrived with regularity that rivaled atomic clocks. Over time, careful measurements revealed that this stability was not absolute, but exquisitely sensitive to the environments through which the signals passed. Every pulse carried both the mark of its source and the trace of its journey across the galaxy. The pattern of arrivals, those millisecond intervals repeated over years, became a map of time itself. Measuring these intervals turned pulsars into natural laboratories for studying not only stellar physics, but also the interstellar medium gravity and even the fabric of space-time. The more carefully the pulses were timed, the more detail they revealed about the cosmos between the pulsar and Earth. The key to pulsar timing lies in the remarkable consistency of rotation. Each turn of the neutron star corresponds to one pulse, and even slight changes in spin rate alter the timing of arrival on Earth. Astronomers record thousands of pulses, compare their arrival times to models of rotation, and detect deviations as small as microseconds. These differences, known as timing residuals, carry a wealth of information. Some result from intrinsic changes within the star glitches, or slowdowns caused by internal dynamics, but others arise from external effects such as motion gravitational interactions or interstellar dispersion. Through these small irregularities, the structure and behavior of the universe are revealed with unparalleled precision. When a pulse travels through interstellar space, it passes through clouds of electrons and ions that delay the signal in a frequency-dependent way. Low-frequency radio waves are slowed slightly more than high-frequency ones, causing the pulse to arrive at different times across the spectrum. This phenomenon, called dispersion, is measured by a value known as the dispersion measure, which represents the total number of free electrons along the line of sight. By analyzing these delays, astronomers can estimate distances to pulsars and map the distribution of plasma throughout the Milky Way. In effect, each pulsar acts as a probe, tracing the invisible structures of ionized gas between stars. Variations in dispersion measure over time even reveal changes in interstellar weather as clouds of electrons drift slowly through the line of sight. The remarkable precision of pulsar timing depends on maintaining stable reference clocks and exact models of the Earth's motion. Because both the observer and the pulsar move, accurate timing requires corrections for orbital motion around the Sun, rotation of the planet, and even tectonic drift. Observatories around the world synchronize their data with atomic time standards, creating networks that observe the same pulsars simultaneously. By combining these measurements, timing errors are reduced to the level of nanoseconds. This collaborative approach, known as pulsar timing arrays, has expanded the role of pulsars from isolated curiosities to instruments capable of detecting ripples in spacetime itself. The sensitivity of these arrays extends beyond interstellar plasma. If a passing gravitational wave stretches space between Earth and a pulsar, the regular arrival of pulses will shift slightly, arriving earlier or later than predicted by a fraction of a microsecond. By monitoring dozens of pulsars spread across the sky, astronomers can search for correlated timing patterns indicating that space itself has been momentarily distorted. Such signals would reveal the presence of gravitational waves from distant merging supermassive black holes. In this way, pulsars serve as galactic-scale detectors, their stability allowing humanity to listen to the slow, deep vibrations of the universe. Even without gravitational waves, timing reveals subtle phenomena. The orbits of binary pulsars, for example, can be tracked with extraordinary detail through pulse arrival times. Each time the pulsar moves toward or away from Earth, its signals are shifted slightly by the Doppler effect. Over months and years, these shifts trace out orbital motion, allowing precise measurements of companion masses and orbital decay due to gravitational radiation. The double pulsar system, PSR J07373039, where both stars emit pulses, has provided direct confirmation of Einstein's theory of general relativity and strong gravitational fields. The loss of orbital energy matches theoretical predictions within tiny margins, showing how timing can weigh gravity itself. Pulse stability also makes pulsars ideal tools for measuring cosmic distances. By comparing dispersion measures across different lines of sight and calibrating them with independent distance estimates, astronomers have built models of electron density throughout the galaxy. Pulsars in globular clusters or near the galactic center further refine these maps. Some even serve as navigation beacons for spacecraft. The regularity of their signals provides a natural coordinate system that could guide autonomous navigation far from Earth, much as sailors once used the stars. On shorter timescales, timing reveals small-scale variations known as scintillation. As radio waves pass through turbulent plasma, they interfere and scatter, producing flickering patterns similar to the twinkling of starlight seen through Earth's atmosphere. These variations can occur over minutes or hours and carry information about the size and motion of irregularities in the interstellar medium. Monitoring scintillation allows astronomers to measure relative velocities between Earth, the pulsar, and the scattering material, offering a dynamic view of galactic plasma flows. The pulsar's signal, stable at its origin, becomes a tracer of cosmic turbulence along its path. Precision timing depends heavily on the purity of signal detection. Pulses are faint, often buried in background noise, and must be averaged over many rotations to extract meaningful data. Modern radio telescopes use digital correlators to align and combine signals from different antennas, enhancing sensitivity and reducing uncertainty. The resulting profiles are compared with high-fidelity templates, and any deviation is recorded as a residual. These residuals accumulate into datasets spanning decades, forming some of the most accurate long-term measurements ever made. Each pulsar becomes a chronometer, and together they form a galactic network of clocks. Despite their precision, pulsars are not perfect. Small irregularities called timing noise appear in many young pulsars, likely caused by internal processes such as vortex motion in the superfluid core or changing currents in the magnetosphere. Unlike glitches, which are sudden and discrete, timing noise produces slow wanderings in spin rate. Correcting for these variations requires careful modelling, but also offers an indirect glimpse into the star's interior dynamics. By studying such deviations, scientists can infer how angular momentum is exchanged between the crust and the superfluid, beneath linking microscopic physics to macroscopic timing. The combination of extraordinary precision and environmental sensitivity makes pulsars unique among astronomical objects. Their signals travel through and are modified by every layer of the cosmic medium gravitational fields, plasma clouds and magnetic turbulence, all imprinted subtly on their timing. In decoding those imprints, astronomers have turned pulsars into tools for measuring the universe with exquisite accuracy. What began as mysterious rhythmic signals now serves as a galactic standard of time. Each pulse, arriving across millions of years and thousands of light years, brings with it a message written in microseconds, a record of motion, distance, density, and change. Through the study of their timing and dispersion, pulsars have transformed from curiosities into the metronomes of cosmic measurement, their precision unmatched and their rhythm enduring across the vastness of space. Every pulsar is born spinning rapidly, but no rotation can last unchanged forever. Over time, the neutron star loses energy through electromagnetic radiation and particle winds, causing its spin to slow gradually. This deceleration, known as spin down, follows a predictable pattern determined by the star's magnetic field strength and the way energy is carried away from its rotation. Young pulsars, still highly magnetized and energetic, lose rotational energy quickly, while older pulsars slow down much more gradually. Each rotation emits a small fraction of the star's stored kinetic energy, converted into radio pulses, X-rays, and relativistic particles. By measuring the rate of slowdown, astronomers can estimate a pulsar's characteristic age and magnetic field intensity. Yet this steady decline hides moments of sudden irregularity, brief sharp jumps in rotation known as glitches that reveal deep secrets of the star's internal structure. The continuous slowdown of a pulsar is remarkably stable for years at a time. Its period increases at a steady rate, often measured in billionths of a second per day. This regularity allows pulsar astronomers to predict future pulse arrival times with extraordinary accuracy. The process resembles a clock whose hands slow imperceptibly but never falter. However, within this long-term trend lie abrupt events that defy the pattern. During a glitch, the pulsar's rotation suddenly accelerates by a tiny amount, sometimes only 1 part in a million, before slowly returning toward the previous rate. These glitches are brief but unmistakable, standing out as sharp steps in the timing record. Their origin lies not in external forces but deep within the star itself, in the interaction between its solid crust and the superfluid interior that lies beneath. Inside the neutron star, the outer crust is composed of dense atomic nuclei, arranged in a crystalline lattice, while the inner regions form a superfluid of neutrons. In a normal fluid, rotation occurs as a bulk motion, but in a superfluid it takes place through the formation of quantized vortices, microscopic whirlpools that carry discrete amounts of angular momentum. These vortices are pinned to the crustal lattice, anchoring the superfluid's rotation to the solid outer layers. As the pulsar slows, the crust loses angular momentum more quickly than the pinned superfluid. Over time, a difference builds between the rotation rates of the two regions. When the tension becomes too great, the vortices suddenly unpin, transferring angular momentum from the superfluid to the crust. The crust speeds up slightly, producing the observed glitch. After a glitch, the pulsar's rotation gradually returns to its long-term slowdown trend, a process known as relaxation. The details of this recovery vary from one pulsar to another, revealing differences in internal structure and superfluid behavior. In some cases, relaxation takes hours, in others it may last months. These timescales reflect how easily the interior fluids can exchange momentum and how strongly the vortices reattach to the lattice. By studying glitch sizes and recovery rates, scientists infer the viscosity, elasticity, and coupling strength within the neutron star properties, impossible to measure in any laboratory. Each glitch acts as an experiment conducted by nature, exposing the hidden physics of dense matter under pressures greater than those inside atomic nuclei. Not all pulsars glitch with the same frequency or amplitude. Young pulsars, such as the one in the Vela constellation, exhibit large and regular glitches, sometimes several per decade. Older pulsars show smaller, less frequent ones, while millisecond pulsars spun up through accretion rarely glitch at all. This pattern supports the idea that the crust and superfluid evolve with age. As temperature drops and magnetic fields weaken the coupling between layers, changes making large-scale unpinning events less likely. The diversity of observed behavior across the pulsar population reflects the variety of internal states among neutron stars. Some appear to release their stored tension suddenly. Others dissipate it, gradually producing continuous micro-adjustments too small to detect individually. The spin-down process itself is governed by magnetic braking. As the rotating magnetic field interacts with surrounding plasma, it emits electromagnetic waves that carry away angular momentum. The torque acting on the star is proportional to the square of the magnetic field strength and the cube of the rotation rate. This means that rapidly spinning, strongly magnetized pulsars lose energy faster than slower or weaker ones. The resulting relationship between spin period and spin-down rate forms the basis of the pulsar PP dot diagram, a map of their evolutionary pathways. On this diagram, young energetic pulsars occupy the upper left, while older slower ones drift toward the lower right. Somewhere along this path, some pulsars cross the boundary into the so-called death line, where their magnetic fields can no longer sustain radio emission. Glitches temporarily reverse this slow march toward inactivity. When the crust speeds up, the pulsar appears younger in rotational terms, momentarily jumping upward in the diagram. The stored angular momentum released by the superfluid replenishes the crust's spin, delaying its decline. The effect is minor in scale, but significant in understanding the physics of neutron stars. In a single glitch, the star releases energy comparable to a large terrestrial earthquake. Yet unlike earthquakes, these events occur under conditions of near-absolute density, with the motion limited to microns across regions kilometers thick. Observing such minute changes from across thousands of light-years highlights the extraordinary sensitivity of pulsar timing techniques. Occasionally, glitches are accompanied by changes in the pulsar's emission profile. In some cases, the pulse shape or intensity shifts, suggesting a reconfiguration of the magnetosphere linked to the internal event. This connection hints that the magnetic field crust and interior superfluid are coupled dynamically. A sudden crustal movement may distort the magnetic axis, altering how the beam sweeps across space. The correlation between spin changes and radiation variations remains an active area of research, offering a rare bridge between internal and external astrophysical processes. Not all rotational irregularities fit neatly into the glitch model. Some pulsars experience gradual wandering in spin rate known as timing noise. This phenomenon likely arises from small-scale interactions within the magnetosphere or changes in torque applied by the electromagnetic field. Timing noise can obscure the detection of smaller glitches, but its presence also provides insight into the pulsar's magnetic activity. In millisecond pulsars where the magnetic field is weak and rotation, stable timing noise is minimal, making them ideal for high-precision experiments such as gravitational wave detection. In contrast, young pulsars exhibit larger fluctuations reflecting their dynamic interiors and strong magnetic fields. The overall evolution of a pulsar's spin can thus be viewed as a dialogue between stability and disturbance. Rotation provides the clockwork precision that defines these stars, while glitches and noise punctuate that rhythm with signs of hidden complexity. Each deviation, however small, is valuable, revealing the dynamic processes beneath the crust. The data accumulated from decades of timing observations across hundreds of pulsars form a collective chronicle of rotational evolution, recording how neutron stars age, cool, and adjust internally. Through the study of spin evolution and glitches, pulsars become windows into the behavior of matter under extremes of density, temperature, and magnetism. They demonstrate that even the most stable systems in the universe are never entirely static. Beneath the calm rhythm of their pulses, stresses build and release in cycles of motion, too small to see yet vast enough to shake the timing of light itself. The balance between slow decay and sudden renewal defines their lives, turning each pulsar into a record of how energy, structure, and time interact in one of nature's most extraordinary machines. Not all pulsars live alone in the emptiness of space. Many orbit a companion star bound by gravity in systems that reveal new layers of astrophysical complexity. In these binaries, the neutron star and its partner form a dynamic exchange of matter, momentum, and energy that can reshape both objects over millions of years. The interplay between gravity and rotation transforms quiet neutron stars into brilliant X-ray sources and eventually into millisecond pulsars, the fastest spinning natural clocks in the known universe. Through these systems, astronomers witness how the same physical laws that govern ordinary stars evolve under the most extreme conditions imaginable. Binary pulsars come in several varieties depending on the mass and stage of the companion. In high-mass systems, the partner is often a hot luminous star still fusing hydrogen in its core. Its strong stellar winds blow continuously into space, and the neutron star captures part of this outflow. The inflowing gas accelerates in the pulsar's gravitational field, forming a stream or disk that spirals inward at enormous speed. As the material falls toward the neutron star, gravitational potential energy converts into heat, producing intense X-rays detectable across great distances. These are X-ray binaries, celestial laboratories where matter experiences the extremes of gravity, compression, and radiation before merging with the neutron star's surface. In lower mass systems, the process occurs more gently but over longer timescales. The companion star, often similar to the Sun, evolves off the main sequence and expands into a red giant. When it fills its Roche lobe, the region where its gravity balances the pull of the neutron star gas begins to stream directly from the companion surface toward the dense remnant. This material does not fall straight in. Conservation of angular momentum forces it to form an accretion disk, a flattened spiral of superheated gas orbiting the neutron star at thousands of kilometers per second. Friction within the disk heats the gas to millions of degrees, causing it to glow in X-rays. Over time, this steady accretion transfers both mass and angular momentum to the neutron star, gradually spinning it up to extraordinary rotation rates. This spin-up process transforms a once slow neutron star into a millisecond pulsar. The transfer of angular momentum acts like a hand turning a wheel, accelerating the rotation until the pulsar completes hundreds of revolutions per second. The same magnetic field that once slowed the pulsar now interacts with the inflowing plasma, balancing the inflow with magnetic pressure. When the magnetic field becomes strong enough to halt accretion, the system transitions from an X-ray source to a radio-emitting pulsar. The beam reignites, but now it rotates hundreds of times faster and with astonishing stability. These recycled pulsars represent a later evolutionary stage where the energy of accretion has rejuvenated the star. Binary systems also provide some of the most precise tests of gravitational physics. In systems where both stars are compact, such as a neutron star paired with another neutron star or a white dwarf, their mutual orbit can be measured through changes in pulse arrival times. The orbital motion produces tiny variations in the timing, allowing astronomers to determine orbital parameters with exquisite precision. The discovery of the first binary pulsar, PSR B91+16, provided direct evidence of gravitational wave emission decades before detectors existed. Its orbit was observed to shrink gradually at exactly the rate predicted by Einstein's general relativity, as energy leaked away in the form of gravitational radiation. Later discoveries of double pulsar systems confirmed these effects with even higher accuracy, establishing pulsar binaries as cosmic laboratories for testing gravity in strong field regimes. The interaction between a pulsar and its companion can take many forms. In some cases, the pulsar's energetic wind strips material from the companion, gradually eroding it until little remains. These systems are called black widows and redbacks, depending on the mass of the surviving companion. The name reflects the destructive nature of the pulsar's radiation, which heats one side of the companion surface to thousands of degrees, while leaving the opposite side cool and dark. As the pulsar's beam sweeps through space, the system flickers in brightness, showing the interplay of energy transfer and orbital geometry. Such systems demonstrate that neutron stars do not merely receive matter, they can also destroy it through relentless radiation and wind pressure. Accretion itself is a highly structured process governed by magnetic fields. Near the neutron star's surface, the magnetic field channels the inflowing plasma toward the magnetic poles, forming bright hotspots where material crashes into the surface at significant fractions of the speed of light. Each impact releases an immense burst of X-rays modulated by the star's rotation. Observed from Earth, this produces X-ray pulsations synchronized with the neutron star's spin, allowing astronomers to measure rotation directly. The luminosity of these X-ray pulsars can exceed 100,000 times that of the Sun, yet it is sustained by matter, falling at only a few tons per second, an indication of the enormous efficiency of gravitational energy conversion near compact objects. In some systems, the accretion rate varies cyclically. When too much material accumulates in the disk, it becomes unstable and dumps a sudden wave of gas onto the neutron star, producing an outburst of X-rays that can last for days or weeks. Afterward, the disk cools and refills, beginning the cycle again. These transient sources help explain how neutron stars gain spin in discrete episodes rather than through constant feeding. Observations of such outbursts reveal how angular momentum is redistributed and how the star's magnetic field reacts to the changing inflow. Binary pulsars also evolve through mass exchange. As accretion continues, the companion star loses material and may eventually become a low-mass white dwarf. The orbit widens as mass is lost, stabilizing into a long-term configuration. In these mature systems, the pulsar remains active as a millisecond beacon, while the white dwarf cools slowly beside it. The contrast between the two objects, one ultra-dense and spinning furiously, the other dim and inert, illustrates the full range of stellar evolution, compressed into a single binary. Some of these pairs persist for billions of years, their orbital dance continuing long after both stars have exhausted their original fuel. Interactions in binaries can also produce exotic phenomena. In rare instances, a neutron star in a tight orbit around a massive companion can trigger a second collapse. When accreted matter pushes it beyond the maximum mass allowed by neutron degeneracy pressure, forming a black hole. In other cases, gravitational interactions between multiple companions can eject one star entirely, sending a runaway pulsar speeding through space at hundreds of kilometers per second. These extremes show that binary systems are crucibles of transformation, capable of turning ordinary stars into some of the most extreme objects in existence. In the quiet aftermath of accretion, when the flow of matter ceases, the neutron star stabilizes as a recycled pulsar. Its rotation, maintained by the spin-up process, remains almost perfectly steady, making it an ideal timekeeper for decades or centuries. The companion, now stripped and cooled, becomes a faint partner in an otherwise serene system. The violence that once defined their interaction fades, leaving behind precision, regularity, and calm. Through binaries, the pulsar's story expands beyond isolation. It becomes part of a shared evolution, where gravity, magnetism, and time weave together to create cycles of destruction and renewal. Each orbit, each pulse, and each brief flare of accretion tell the same quiet truth, that even in the deepest extremes of physics, balance emerges and the motion of matter and light continues in an endless exchange across the gulf of space. Among the thousands of pulsars scattered through the Milky Way, a select few exist in orbits so compact that they serve as natural laboratories for testing the most profound aspects of physics. These relativistic systems, where gravity operates in its strongest measurable form, short of a black hole, reveal how space-time behaves under extreme curvature. Each pulse from such a system carries a record of its orbit, its velocity, and the gravitational potential in which it moves. When these pulses are timed with microsecond accuracy, they confirm predictions of general relativity and expose minute deviations that might signal new physics. Pulsars thus bridge the scale between quantum structure inside their cores and the geometry of the cosmos that defines their motion. The first major breakthrough came with the discovery of the binary pulsar Pulsar B191316 in the 1970s. It consists of a neutron star and an unseen companion, likely another neutron star locked in an orbit only a few hours long. By recording the arrival times of its pulses, astronomers reconstructed its orbital motion with astonishing precision. They found that the orbit was slowly shrinking, not because of any visible drag, but due to the emission of gravitational waves ripples in spacetime carrying energy away. The measured rate of orbital decay matched Einstein's theoretical prediction with remarkable accuracy, offering the first indirect proof that gravitational waves exist. Decades later, direct detection by interferometers confirmed this conclusion, but the pulsar had already shown the way. The extraordinary stability of pulsar timing makes these systems ideal for probing relativistic effects. In close orbits, time dilation and gravitational redshift alter the rate at which pulses arrive on Earth. When the pulsar moves deeper into the gravitational potential of its companion, its clock runs slightly slower, shifting the pulse frequency. As it moves away, the effect reverses. Over each orbit, these changes form a pattern precisely described by relativity. Similarly, the shape of the orbit itself deviates from classical expectations. The elliptical path of a relativistic binary precesses, meaning that its orientation in space rotates gradually over time. The rate of this precession depends on both masses and provides another stringent test of gravitational theory. The double pulsar system, PSR J0737-3039, has extended these tests further. Both neutron stars in the pair emit detectable pulses, allowing astronomers to observe two rotating clocks orbiting each other. This unique configuration permits simultaneous tracking of both objects and direct measurement of effects such as gravitational time delay, orbital decay, and relativistic spin precession. Each parameter aligns precisely with the equations of general relativity. The system's orbital period shortens by mere microseconds per year, yet this minute shift corresponds exactly to the energy expected to be radiated as gravitational waves. No other natural system allows such direct observation of relativistic motion sustained over millions of cycles. In these binaries, the gravitational field is so intense that space around the stars is significantly curved. Light emitted from one pulsar must traverse this warped spacetime to reach Earth, and as it does, it experiences additional delays known as the Shapiro delay. This effect depends on the orbital geometry and the mass of the companion star. Measuring it provides one of the most accurate determinations of neutron star masses available. In some systems, the Shapiro delay amounts to only a few tens of microseconds, yet that tiny deviation reveals the precise structure of the orbit and the curvature of spacetime between the two stars. Beyond confirming relativity, relativistic pulsar systems also help constrain the equation of state of dense matter. Precise mass measurements show how much matter can be packed into a neutron star before collapse into a black hole becomes inevitable. Observations of pulsars approaching 2 solar masses indicate that neutron matter can withstand extraordinary pressures, ruling out many theoretical models. Future discoveries of even more massive examples could further refine these limits, linking gravitational tests to nuclear physics deep within the stars. Some pulsars orbit more exotic companions. In systems containing white dwarfs, the pulsar's gravity slightly distorts the smaller star, creating measurable variations in orbital timing. In others, the companion may be a black hole, providing an even stronger gravitational environment for testing theory. Although no confirmed pulsar black hole binary has yet been observed, their eventual discovery would allow measurement of frame dragging and other effects predicted by relativity near the boundary of a black hole's event horizon. Search efforts continue as such a system would represent the ultimate astrophysical laboratory for studying gravity. Relativistic motion also affects the orientation of the pulsar's spin axis. Over time, the intense gravitational interaction between the two neutron stars causes relativistic spin-orbit coupling, making each spin axis precess around the total angular momentum of the system. This precession slowly alters the direction of the pulsar's radio beam. Observers on Earth may see the pulses fade and eventually disappear as the beam moves out of view, only to return decades later as the precession continues. This geometric dance, observed in several systems, offers a rare glimpse of the dynamic link between rotation magnetism and gravity in compact stars. The precision of these measurements extends to the millisecond level. Every pulse acts as a marker, and the cumulative timing residuals after thousands of orbits define parameters with astonishing accuracy. These data have allowed scientists to test not only general relativity, but also alternative theories of gravity, many of which predict subtle deviations in orbital decay or time delay. So far, all tests have reinforced Einstein's model, confirming that spacetime behaves as predicted, even under gravitational fields a billion times stronger than those near the Sun. Yet the very act of measuring with such precision keeps open the possibility of discovery. Any deviation, however small, could signal new physics. The same techniques used in binary pulsars are now applied on a galactic scale. Networks of millisecond pulsars form pulsar timing arrays that monitor the timing of dozens of stable sources simultaneously. By comparing the timing residuals across the sky, astronomers can detect correlated patterns caused by passing gravitational waves from distant merging supermassive black holes. In this way, pulsars scattered throughout the Milky Way become components of a single observatory spanning thousands of light years. The first indications of a low-frequency gravitational wave background have already emerged from these efforts, confirming that the universe continually vibrates with the echoes of colossal mergers far beyond individual galaxies. Relativistic pulsar systems remind us that the same physics governing atomic clocks and laboratory experiments applies seamlessly across cosmic scales. The pulsar's immense gravity, rapid rotation, and precision timing compress the equations of relativity into observable form. Each pulse arrival, delayed or advanced by millionths of a second, represents a conversation between matter and space-time, a dialogue spoken in the language of geometry and motion. Through these systems, the universe offers its own proof of order, showing that even under extremes of mass and velocity, the structure of time and space remains coherent. In the silent reaches of the galaxy where two neutron stars orbit in tight embrace gravity, Ben's light slows time and carries energy away as waves across the cosmic sea. The pulses we record on Earth are the distant echoes of that motion translating curvature into rhythm. As measurements continue to sharpen these relativistic laboratories, we'll keep testing the foundations of physics, perhaps someday revealing limits to the theories that have so far held true. For now, each pulse stands as a quiet affirmation of the harmony between observation and theory, between rotation and gravity, between the relentless spin of collapsed stars and the space-time they so elegantly warp. Around many pulsars lies a faint yet vast structure, the Pulsar Wind Nebula. These glowing clouds are shaped not by light, but by the relentless flow of particles and magnetic fields streaming outward from the neutron star. The same rotation and magnetism that generate the pulsar's beams also drive a continuous wind of high-energy electrons and positrons. Moving at nearly the speed of light, these charged particles expand outward, collide with surrounding gas, and create shock fronts that radiate across the electromagnetic spectrum. The resulting nebula marks the boundary where the pulsar's internal energy meets the external environment of interstellar space. It is both a record of the pulsar's past and an engine that continues to transform its surroundings long after the supernova explosion has faded. The process begins near the light cylinder, where the co-rotating magnetic field can no longer keep pace with the star's rapid spin. Here plasma escapes along open field lines, forming a supersonic outflow that carries away rotational energy. This pulsar wind expands freely until it encounters slower moving material, either the remnants of the supernova or the interstellar medium itself. At this point, the flow abruptly decelerates in a termination shock. The energy lost in that collision converts into heat radiation and magnetic turbulence, producing a luminous bubble of energized particles. Observed through X-ray and radio telescopes, these bubbles appear as intricate filaments and arcs, each one a trace of magnetic field lines illuminated by electrons spiraling within them. The Crab Nebula is the archetype of this process. At its center, the Crab pulsar injects continuous energy into the surrounding gas, sustaining brightness that has endured for nearly 1,000 years. Observations show concentric rings and jets emerging from the pulsar aligned with its rotation axis. The inner ring corresponds to the termination shock, where the wind abruptly slows and becomes visible in X-rays. Beyond that, swirling eddies form as the magnetic field and plasma interact. The entire structure expands slowly into space, its shape changing over years as fresh material streams outward. This dynamic evolution illustrates how rotational energy from a star compressed into 20 kilometers can illuminate a nebula several light-years wide. Each pulsar wind nebula is unique, shaped by the conditions into which the wind expands. Some are spherical and smooth, others elongated or asymmetric depending on the pulsar's motion and the density of surrounding gas. When a pulsar moves through space at high speed, often hundreds of kilometers per second, it carries its wind with it, forming a bow shock, where the outflow meets the oncoming interstellar medium. Behind the moving star, a trail of glowing particles stretches like a comet's tail marking its path. These bow-shock nebulae glow faintly in optical light, and vividly in X-rays, showing that even small pulsars can influence vast regions of space through their winds. The emission from pulsar wind nebulae arises mainly from synchrotron radiation, produced when electrons spiral through magnetic fields at relativistic speeds. This radiation spans from radio to gamma rays, with brightness peaking at wavelengths that depend on particle energy and field strength. As electrons lose energy over time, the spectrum softens, revealing how the pulsar's output changes with age. In young systems like the Crab, the emission extends to high energies, while in older ones the radiation shifts toward radio and infrared. By studying these spectra, astronomers can determine the rate at which pulsars convert rotational energy into particle acceleration, and trace the lifetime of magnetic activity around them. At the interface between the pulsar wind and the outer medium complex, hydrodynamic and magnetic processes unfold. The wind, though relativistic, behaves like a fluid subject to instabilities and turbulence. Magnetic reconnection, where field lines break and reconnect, can accelerate particles to even higher energies, creating localized flares. In the Crab Nebula, sudden brightening events have been observed in gamma rays, indicating that such reconnection can release vast amounts of energy in short bursts. These phenomena show that even centuries after a supernova explosion, the environment around a pulsar remains active and evolving, driven by invisible but powerful electromagnetic forces. The structure of a pulsar wind nebula evolves as the pulsar ages. Initially, the nebula is confined within the expanding supernova remnant, its pressure balanced by the hot gas of the explosion. As the remnant cools and disperses, the pulsar wind breaks free into the surrounding interstellar medium. In this later phase, the nebula may fade or change shape, but it continues to inject relativistic particles into the galaxy. These particles contribute to the population of cosmic rays that pervade space, carrying traces of their origin in pulsar magnetospheres. In this way, pulsar winds serve as a bridge between compact stellar remnants and the diffuse cosmic environment. Observations across different wavelengths have revealed multiple layers within these nebulae. Radio maps show the large-scale structure of older, cooler electrons. Optical and X-ray images trace the inner regions where freshly accelerated particles emit higher energy light. Each wavelength corresponds to a distinct population of particles, giving a time-lapse view of the pulsar's activity. Over decades of observation, astronomers have recorded gradual changes in brightness and shape, demonstrating that pulsar wind nebulae are dynamic systems, not static relics. The constant input of energy from the pulsar maintains their motion, ensuring that they evolve even as the star itself slowly spins down. Some pulsars produce winds powerful enough to interact directly with nearby molecular clouds or star-forming regions. The shock waves from their outflows compress surrounding gas, sometimes triggering new generations of stars. Thus, the death of one massive star can indirectly contribute to the birth of others. The feedback loop between pulsar winds and galactic ecology connects the smallest scale of matter, the neutron star, to the largest patterns of cosmic evolution. Every energetic particle emitted from the pulsar carries energy that may one day influence distant gas-linking events across millions of years and light years. In binary systems, pulsar winds interact with material from companion stars, producing additional complexity. When a pulsar's radiation collides with an accretion flow or stellar wind, it can create localized shocks that emit both X-rays and gamma rays. Some of these interactions are periodic, varying with the orbital motion, while others are erratic depending on magnetic field orientation. These systems highlight the versatility of pulsar winds, capable of shaping environments ranging from isolated nebulae to dense binary interactions. The study of pulsar wind nebulae continues to refine our understanding of how energy flows through the universe. They illustrate the long reach of a neutron star's rotation energy that begins as mechanical spin and ends as diffuse radiation filling light years of space. Their filaments and arcs trace the invisible architecture of magnetic fields, revealing the unseen patterns of cosmic magnetism. In them, astronomers observe matter transformed into light and motion sustained by the faint hum of a rotating core. In the silence between stars where remnants of explosions drift, the glow of a pulsar wind nebula endures. It is the afterimage of stellar death turned into radiance, the mark of a star that continues to act long after its destruction. Every wisp of light, every filament of charged particles tells of a heartbeat, still pulsing at the center, a neutron star spinning endlessly, feeding its surroundings with invisible streams of energy. These nebulae remind us that even in decay, motion persists, and that the faint winds of a collapsed star can shape the light of galaxies far beyond their own reach. Beneath the thin crust of a neutron star lies a realm of matter, unlike anything known elsewhere in the universe. Here atomic nuclei dissolve, and the familiar distinction between individual particles fades. The immense gravity compresses matter beyond the density of an atomic nucleus, forcing protons and electrons to combine into neutrons, and releasing vast numbers of neutrinos in the process. What remains is a substance governed by the principles of quantum mechanics and nuclear physics, a form of matter that challenges every model developed in laboratories on Earth. Understanding this interior is essential to understanding everything a pulsar does, from its rotation and magnetic field to the way it glitches and cools with time. The outermost layer, only a kilometer thick, is a crust of atomic nuclei, arranged in a lattice embedded in a sea of electrons. Despite its incredible density, this crust behaves like a solid capable of supporting starquakes when magnetic or rotational stresses build. The pressure increases rapidly with depth, and the spaces between nuclei vanish as atoms are squeezed together. Deeper still, at densities approaching those of the atomic nucleus, neutrons begin to drip out of the nuclei, forming a neutron-rich fluid that fills the gaps. This region marks the transition from conventional nuclear matter to the exotic forms that dominate the inner star. Below the crust lies the outer core, a dense fluid composed mainly of neutrons with small fractions of protons, electrons, and possibly muons. Under these extreme pressures, the strong nuclear force becomes repulsive at short ranges, balancing gravity and preventing further collapse. The particles are so densely packed that they obey quantum degeneracy, a rule preventing identical fermions from occupying the same state. This degeneracy pressure provides the counterforce to gravity that allows neutron stars to exist. Yet the composition and behavior of this fluid are still uncertain. Theories suggest that neutrons may form pairs similar to electrons in superconductors, creating a superfluid that flows without friction. The protons, though fewer in number, may form a superconducting network that carries magnetic fields through the interior with perfect conductivity. This combination of superfluidity and superconductivity has profound consequences for a pulsar's observed behavior. The superfluid component rotates through an array of quantized vortices, each one carrying a discrete amount of angular momentum. These vortices anchor to the crust and can slip suddenly, producing the rotational glitches seen in timing data. The superconducting protons lock magnetic field lines into quantized flux tubes that move and interact with the neutron vortices, linking magnetic evolution to spin dynamics. Together, these quantum phenomena control how the pulsar's interior stores and releases energy over time. They also determine how heat and momentum are transported from the core to the surface, influencing cooling rates and long-term stability. Deeper within, the core conditions grow even stranger. As density increases towards several times nuclear saturation, the standard models of nuclear matter begin to fail. Protons and neutrons may dissolve into their constituent quarks, forming a sea of up-down and possibly strange quarks, a state known as quark matter. In this hypothetical inner core, matter would behave more like a fluid of fundamental particles than a collection of composite ones. Some theories propose that these quarks might pair into a color superconducting state, a phase predicted by quantum chromodynamics, but never observed directly. If such matter exists, it could alter the star's mass-radius relationship, allowing higher masses or smaller radii than would otherwise be possible. Detecting its signature would provide an unprecedented test of fundamental physics. Observations of neutron star masses and radii offer indirect clues to their interior composition. Using X-ray observations of pulsars in binary systems, astronomers can measure how the surface temperature and luminosity change as the star cools. The rate of cooling depends on how efficiently neutrinos escape from the core, which in turn depends on the available particle interactions. Rapid cooling suggests exotic processes such as direct Urca reactions, where neutrons convert directly into protons and electrons, emitting neutrinos freely. Slower cooling indicates that these processes are suppressed, consistent with the presence of superfluidity. By comparing models to observed surface temperatures of young neutron stars, researchers infer that both superfluid and superconducting states likely exist, shaping the star's thermal evolution. Seismic activity within the crust also provides hints about internal structure. When magnetic stress accumulates or rotational strain exceeds the crust's strength, sudden shifts occur, producing starquakes. These events may alter the star's moment of inertia, slightly contributing to observed glitches. The vibrations excited by such quakes propagate through the interior as oscillations detectable in X-rays during magnetoflares, offering a rare opportunity to probe the neutron star's density profile. By analyzing these oscillations, scientists can estimate the thickness of the crust and the rigidity of the inner layer's quantities, directly linked to the equation of state of dense matter. The challenge of understanding these interior states lies in the absence of direct observation. Laboratory experiments can reproduce densities up to the edges of atomic nuclei, but not beyond. Particle accelerators and heavy ion collisions simulate fleeting moments of high density and temperature, yet neutron stars exist in the opposite regime, cold, steady, and immensely dense. Theorists therefore rely on extrapolations of nuclear models and on observational constraints from astrophysics. Each new measurement of a pulsar's mass or radius narrows the possible range of equations of state. When the gravitational wave event GW170817 revealed the merger of two neutron stars, the resulting tidal distortions provided additional clues, showing that neutron matter is relatively stiff and resists compression, ruling out the softest equations of state. The interplay between theory and observation continues to refine our picture of the neutron star interior. Future missions aim to measure surface hotspots, pulse profiles, and X-ray spectra with enough precision to infer the star's size to within a few hundred meters. Combined with mass estimates from relativistic binaries, these data will map the relationship between mass and radius across different stars. Each point on that curve represents a window into the behavior of matter at nuclear and subnuclear densities. When the curve bends or flattens, it signals a change in composition, perhaps the onset of quark matter or another exotic phase. Inside the neutron star, time and temperature evolve slowly. Over millions of years, the core cools, the crust becomes more rigid, and magnetic fields drift as flux tubes migrate through the superconducting interior. This evolution changes the pulsar's external behavior, subtly altering its spin-down rate and emission. In this way, the hidden interior continues to shape what can be observed from light years away. The interplay between deep quantum states and macroscopic motion makes neutron stars unique. They are single objects where fundamental forces, gravity, electromagnetism, and the strong nuclear force all balance simultaneously. Though no probe can yet penetrate a neutron star, its pulse rotation and temperature act as messengers from within. Every observed glitch, every cooling curve, and every limit on mass and radius is a coded message from matter under conditions beyond experiment. The interior of a neutron star remains the most extreme continuous environment known, a living remnant of a collapsed core that compresses the universe's fundamental particles into a single coherent state. Beneath the crust, beyond the reach of light, the neutrons flow in silence. The protons glide through magnetic flux, and perhaps at the very center, quarks drift freely in a sea that no laboratory can reproduce. It is within this invisible core that the essence of pulsars resides, a steady balance between gravity and quantum pressure, an equilibrium so perfect that it can spin for millions of years without losing its form. To understand pulsars with the precision their rhythms deserve, astronomers have built a global network of instruments capable of measuring their signals to within millionths of a second. These observation and timing arrays combine data from radio telescopes across continents, transforming individual observatories into a single coordinated ear listening to the galaxy. From the earliest days of pulsar research, timing accuracy has steadily improved as technology evolved from analog recorders to atomic clocks and digital correlators. What began as a simple detection of repeating radio pulses has grown into a field that now measures variations so small that they can reveal the passage of gravitational waves or the slow drift of Earth's orbit through space. Observation has become both art and precision engineering, merging human patience with the stability of the universe's most reliable clocks. Modern pulsar observation relies primarily on radio telescopes which detect the low-frequency signals emitted by most pulsars. Large dishes such as those at parks in Australia, Arecibo in Puerto Rico before its collapse, Effelsberg in Germany, and the Green Bank Telescope in the United States have been instrumental in expanding the known pulsar catalogue. By scanning the sky systematically, these instruments identify faint periodic sources that repeat with consistent timing. Once discovered, pulsars are observed regularly, sometimes daily, to maintain precise timing records. The raw data, consisting of radio intensity as a function of time and frequency, is processed to remove interference correct for dispersion caused by interstellar electrons and align the pulses into stable average profiles. These profiles serve as templates against which future signals are compared, allowing measurement of any minute differences in arrival times. The resulting timing data form the backbone of pulsar astrophysics. Each observation yields a time of arrival, or TOA, corrected to the reference frame of the solar system's barycenter, the center of mass around which all planets and the Sun orbit. This correction eliminates the influence of Earth's rotation and orbital motion, ensuring that measured variations originate from the pulsar itself or from changes in spacetime between the pulsar and Earth. When TOAs from multiple observatories are combined, they create a continuous timeline extending over years or decades. Subtracting the predicted arrival times derived from models of the pulsar's rotation and motion leaves residuals that highlight deviations. It is within these residuals that the universe reveals its subtleties, gravitational interactions, interstellar disturbances, and cosmic vibrations stretching the very fabric of space. Timing arrays elevate this technique to a new level. By monitoring dozens of millisecond pulsars distributed across the sky, astronomers can detect correlated shifts in their pulse arrival times. A gravitational wave passing between Earth and those pulsars slightly warps space-time, causing all affected signals to arrive early or late in a pattern characteristic of the wave's polarization and direction. Unlike the high-frequency waves detected by ground-based laser interferometers, these long-wavelength ripples arise from orbiting supermassive black holes millions of light-years away. Detecting them requires not milliseconds but decades of precise observation. The North American Nanohertz Observatory for Gravitational Waves, NanoGrav, the European Pulsar Timing Array, and the Parkes Pulsar Timing Array in Australia are among the leading collaborations pursuing this goal. Recently, evidence of a stochastic gravitational wave background has emerged, an undulating cosmic hum likely produced by countless merging galaxies. The discovery transforms pulsars from distant curiosities into instruments for probing the deeper structure of space-time. Beyond gravitational waves, pulsar timing arrays also refine our understanding of time itself. By comparing the rotational stability of pulsars with that of terrestrial atomic clocks, scientists can test the constancy of fundamental physical constants. The best millisecond pulsars exhibit fractional stability over decades that rivals or surpasses man-made clocks, allowing independent checks on the Earth's time standards. This interplay between celestial and laboratory precision has practical implications. Corrections derived from pulsar data contribute to improvements in timekeeping systems that underlie navigation, communication, and scientific measurement. In a sense, pulsars have joined humanity's network of time references, their distant beats synchronized with our own mechanical oscillators. Observation across multiple wavelengths complements these timing efforts. X-ray telescopes such as NISA on the International Space Station measure the thermal emission from pulsar surfaces, providing constraints on their size and temperature. Gamma-ray observatories like Fermi identify high-energy pulsars invisible to radio surveys, revealing populations shaped by different emission geometries. Optical telescopes occasionally detect faint pulsations from nearby sources, while radio interferometers image the nebulae surrounding energetic pulsars. Together, these observations link the external appearance of a pulsar to its internal mechanisms. By studying pulse phase alignment between radio X-ray and gamma-ray bands, astronomers determine where in the magnetosphere each form of radiation originates, refining models of acceleration and emission. The technological demands of pulsar observation continue to drive innovation. Modern backends record vast bandwidths at high sampling rates, producing data streams of terabytes per session. Sophisticated algorithms sift through this data to search for new pulsars, correcting for dispersion and Doppler shifts caused by orbital motion. Machine learning now assists in identifying candidates, while international collaborations share raw data and timing models to ensure uniform calibration. New facilities such as the 500-meter aperture spherical telescope in China and the Meerkat Array in South Africa have already expanded the pulsar inventory dramatically, uncovering rare systems, including binaries eclipsing pulsars and transitional states between accretion and radio emission. Future instruments like the Square Kilometre Array will push sensitivity still further, capable of detecting weaker signals and monitoring thousands of pulsars simultaneously. Timing precision also depends on the stability of Earth's environment. Atmospheric conditions, ionospheric delays, and even tectonic motion can affect measurements at the microsecond level. To mitigate these factors, observatories maintain exact position tracking and correct signals using real-time measurements of atmospheric water vapor and electron content. Data are then transferred to central repositories, where they are combined into global fits. The long-term consistency of these datasets allows subtle phenomena to emerge, patterns invisible in single observations, but clear when decades of timing are aligned. This patience is the hallmark of pulsar science, the discipline of measuring change so slowly that its significance may appear only after generations of observation. In addition to monitoring individual pulsars, timing arrays create an opportunity to study collective behavior. Correlations among pulsars can reveal global effects such as irregularities in Earth's rotation shifts in the solar system's center of mass, due to unmodeled planetary motion, or variations in interstellar dispersion caused by large-scale plasma waves. In this sense, pulsars act as sensors not only of their own physics, but of everything in the line between them and Earth. The entire galaxy becomes a laboratory, with neutron stars serving as timing beacons scattered through its spiral arms. The pursuit of precision timing has also deepened collaboration among observatories worldwide. Coordinated observation campaigns ensure that pulsars are monitored continuously, as Earth's rotation carries each telescope into and out of view. Data are exchanged and cross-checked to eliminate systematic errors. The combined data set spanning multiple continents and decades forms one of the most accurate records of any natural phenomenon in existence. From these records emerge measurements of gravitational waves, tests of relativity, and insights into the interstellar medium. Each contribution, each carefully measured pulse adds to an archive that transcends generations, turning pulsar timing into a cumulative science of extraordinary longevity. Ultimately, the practice of observing and timing pulsars transforms human perception of time and scale. These stars born from catastrophic explosions and compressed to unimaginable densities now function as steady cosmic chronometers. They mark seconds, decades, and cosmic ages with equal precision. Through their signals, astronomers connect the motions of distant galaxies to the tick of terrestrial clocks linking phenomena separated by light years and eons. The global arrays that listen to them embody both technological achievement and cosmic humility, instruments built by humans to hear the quiet rotations of collapsed stars, to measure the ripples of space-time, and to confirm that across the vastness of the universe even the smallest pulses of order can endure. After decades of study, pulsars remain among the most precisely measured yet profoundly mysterious objects in the cosmos. Their discovery transformed the understanding of stellar death, magnetism, and relativity, but each layer of explanation has uncovered deeper uncertainties. Even as global timing arrays detect the faint undulations of gravitational waves and space telescopes resolve their nebulae, the essential workings of these spinning neutron stars still conceal puzzles of matter and motion not yet solved. The frontiers of pulsar science now extend across disciplines linking astrophysics, nuclear physics, and cosmology in a continuous search for what remains hidden inside and around these compact beacons. One of the enduring questions concerns the ultimate fate of pulsars and their long-term evolution. Observations show that rotation slows steadily, yet the exact mechanisms by which energy dissipates remain imperfectly understood. The standard model of magnetic dipole radiation explains much of the spin-down, but discrepancies appear when comparing theoretical predictions to measured rates. Some pulsars lose energy faster than expected, suggesting contributions from particle winds or magnetic field decay. Others slow more gradually, implying complex interactions between crust magnetosphere and radiation. As pulsars age and their magnetic fields weaken, they cross the theoretical boundary known as the death line, where pair production ceases and radio emission falls silent. Whether these extinct pulsars truly become inert or continue faintly in other wavelengths remains uncertain. Detecting them would complete the map of a pulsar's life from its explosive birth to its final whisper in darkness. Equally uncertain is the nature of magnetic field evolution inside neutron stars. Observations of magnetars with fields exceeding 100 trillion Gauss demonstrate that magnetic energy can dominate stellar behavior, reshaping the crust and driving bursts of radiation. Yet the origin of such extreme fields is debated. They may arise from dynamo action during the star's birth, amplified by rapid rotation, or from fossil fields inherited from massive progenitors. Over millions of years, these fields decay through processes such as Hall drift and ohmic dissipation, but the rate and pattern of this decay depend on poorly known conductivity and composition of the crust. Understanding magnetic evolution is vital, not only for explaining pulsar aging, but also for interpreting sudden outbursts, timing irregularities, and the eventual quenching of emission. The composition of neutron star interiors remains another unresolved frontier. Despite advances in nuclear theory, no experiment can replicate the conditions inside these objects. Observations of massive pulsars with nearly twice the Sun's mass challenge many theoretical equations of state that predict collapse at lower densities. The possibility of exotic phases, hyperons, meson condensates, or deconfined quarks remains open. The detection of gravitational waves from neutron star mergers has begun to provide new constraints on these models, revealing how compressible neutron matter truly is. Future observations may identify subtle differences in tidal deformation or post-merger oscillations that distinguish between conventional nuclear matter and more exotic compositions. A definitive answer would link astrophysical observation to the fundamental forces governing matter at subatomic scales. Another open question lies in the origin of the fastest spinning millisecond pulsars. The accepted explanation attributes their rotation to accretion from binary companions, yet the precise limits of this process are unclear. The fastest known pulsar spins more than 700 times per second, approaching the theoretical breakup speed where centrifugal force would overcome gravity. Whether natural processes can push rotation beyond this limit is unknown. Moreover, some millisecond pulsars appear isolated, suggesting that their companions were destroyed or ejected after the recycling phase. Understanding how these systems evolve and whether isolated millisecond pulsars can form by other means remains a key goal for future surveys. Pulsar emission itself still defies complete explanation. The lighthouse model describes the basic geometry, but the microphysics of how radiation is produced, particularly the coherent radio emission, remains elusive. The details of particle acceleration pair cascades and plasma instabilities within the magnetosphere are subjects of active debate. Simulations of pulsar magnetospheres, though increasingly sophisticated, rely on assumptions about plasma supply and field geometry that are not directly observable. The challenge is to reconcile theory with the extraordinary stability of pulse shapes over years, even while accounting for sudden shifts, nulls, or mode changes seen in some pulsars. High-resolution observations at multiple wavelengths continue to refine these models, but a unified explanation connecting radio X-ray and gamma-ray emission is still incomplete. Another frontier extends outward into the galactic environment. Pulsars serve as probes of the interstellar medium, yet the medium itself is complex and dynamic. Long-term timing campaigns reveal variations in dispersion measure that trace drifting clouds of plasma and turbulence along the line of sight. Mapping these fluctuations not only improves pulsar timing, but also builds a three-dimensional picture of the galaxy's hidden structure. As observations accumulate, astronomers are beginning to identify coherent patterns of plasma motion and density, showing that pulsar signals can illuminate the invisible skeleton of ionized gas permeating the Milky Way. Future instruments with higher sensitivity may even detect changes caused by structures at the edge of the galaxy or in the intergalactic medium. On cosmological scales, pulsar timing arrays are poised to open a new window on the universe. The tentative detection of a gravitational wave background marks the beginning of a field that could soon observe the slow choreography of supermassive black holes orbiting in distant galaxies. Each pulsar added to the array sharpens sensitivity, and as data sets grow over decades, the signal of these giant mergers will become clearer. Measuring the spectrum of this background may reveal how galaxies assemble and how black holes evolve at their centers. Beyond that, pulsar timing might one day detect relic gravitational waves from the early universe, offering clues about inflation and the formation of cosmic structure. In this way, neutron stars born from stellar death could help uncover the universe's earliest moments. Even with these grand prospects, some mysteries remain purely local. The distribution of pulsars across the galaxy still appears uneven, shaped by both observational bias and intrinsic dynamics. Their birth velocities vary widely, with some ejected from the galactic plane at hundreds of kilometers per second. The mechanisms behind these kicks are not fully understood. Asymmetries in supernova explosions may play a role, but details remain uncertain. Mapping the true population requires continued surveys capable of detecting faint or distant pulsars, including those whose beams do not point toward Earth, but may emit in other wavelengths. Future exploration will depend on new generations of observatories. The square-kilometre array now under construction will detect tens of thousands of new pulsars, including the first likely pulsar black hole binary. Such a system would provide an unparalleled test of general relativity, probing gravity in conditions stronger than any yet measured. Space-based X-ray and gamma-ray missions will complement these discoveries, resolving the surfaces of neutron stars and measuring their thermal spectra. Together, these instruments promise to extend pulsar science from cataloguing to precise physical modelling, turning each pulsar into a laboratory for fundamental physics. Yet even as technology advances, pulsars remain humbling reminders of nature's depth. Their pulses, steady across millennia, connect the smallest particles to the structure of space-time itself. Each signal we record carries information not just about a single star, but about the laws that shape reality. The unanswered questions about their interiors, their origins, their evolution, and their ultimate silence ensure that pulsar research will continue for generations. The frontier lies not only in new instruments or discoveries, but in the enduring act of listening, of measuring intervals so regular that they transcend the passage of human time. Pulsars endure as both mystery and measurement, collapsing the vastness of the universe into a rhythm that can be counted, recorded, and understood almost.